well known in algebraic topology as the total space, a contractible space, universal bundle. So I will first explain what a universal bundle is. It's very well known in algebraic topology as the total space, a contractible space, universal bundle. So I will first explain what a universal bundle is. It's very well known in algebraic topology as the total space, a contractible space, universal bundle. So I will first explain what a universal bundle is. It's very well known in algebraic topology as the total space, a contractible space, universal bundle. Is the total space of a universal bundle. Okay? So I'm going to define a universal bundle. When you have a fiber bundle over a space, and if you have a mapping into the base space, so I will really explain what a universal bundle is. It's very well known in algebraic topology. You have a fiber bundle as the total space, a contractible space, universal bundle. You have a map is from X to B total space. Then we define the pullback last time of universal. So the pullback bundle is a fiber bundle with the same fiber. So I'm going to define a universal bundle. Now, a universal bundle, when you have a fiber bundle, is a bundle over a space for a group G. And if you have a mapping into the base, so that it's very well known. Every principal G bundle, fiber bundle, can be total space, contractible space. Given any principal G bundle, you have a map. Say P is from over X to B total space. Then there exists. We define the pullback. A map, a continuous map H into the base, so the universal bundle such that the fiber bundle is isomorphic. So I'm going to define a universal bundle. That's a universal bundle. So that's a picture. Now a universal bundle, when you have a definition down in Word, is a bundle over for a group G. And if you have a mapping into the base, so that it's very well known. Every principal G bundle, fiber bundle, can be total space, contractible space. Given any principal G bundle, you have a map. Say P is G over X total space. Then there exists. We define the pullback. A map, a continuous map H into the base, so the universal bundle such that the fiber bundle is isomorphic. So I'm going to define a universal bundle. That's a universal bundle. So that's the picture. Now a universal bundle, when you have a definition down in Word, is a bundle over for a group G. And if you have a map in satisfying two properties, so that it's very well known. Every principal G bundle, fiber bundle, can be total space, contractible space. Given any principal G bundle, you have a map. Say P is G over X over. Then there exists. We define the pullback. A map, we usually take this X to be a CW base, so the universal bundle, because such that the fiber bundle is isomorphic. So I'm going to define a universal bundle, universal bundle. That's a picture. Now a universal bundle, when you have a cells, is a bundle over for a group G over the CW. And if you have a map in satisfying two properties, so that it's very well known. Every principal for any principal bundle for any total space, contractible space, given any principal G bundle, you have a map. from X to P is G over X, okay, over, then there exists, we define the pullback so that a map, we usually take this X to be a theta base, so the universal bundle, because such that P is isomorphic to the, so I'm going to define a universal bundle, universal bundle. That's a picture. Now a universal bundle, when you have a cell, that's the first bundle, okay, for a level something about writing mathematics. And if you have when you see that you have a set every, it's very well known, every principle, for any principal bundle change that any total space, intractable space, even any principal G bundle in the map, from X, and then there's a second property over, then we define the pullback so that a map, if you have two take this X to be a theta base, so the H0 such that P is isomorphic, so I'm going to define a universal bundle. That's a picture now. Now a universal bundle, when you have a cell, that's the first bundle, okay, for a level something about writing mathematics. And if you have when you see that you have a set every, it's very well known, every principle, for any principal, then the two maps are any total space, intractable space, even any principal G bundle in the map, from X, and then there's a second property over, then we define the pullback so that a map, if you have two take this X to be a theta base, so the such that there is a theorem so I'm going to define that's a picture now a universal bundle, when you have a cell, that's the first bundle, okay, for a level something about writing mathematics. And when you see that you have a set every, it's very well known, every principle, for any principal, then the two maps are any total space, intractable space, even any principal G bundle in the map, from X, and then there's a second property over, then we define the pullback so that, and if you have two take this X, what that means is theta base, so the such that there is a theorem that's a picture now, a universal bundle, when you have a cell, that's the first bundle, okay, for a level space not necessarily see that you have a set every universal for any principal, then the two maps are any total space, even any principal G bundle in the map. But and then if it's there's a second property, then we define the, so if you have two maps, and if you have mapping into B, and E over B, okay, is principal G bundle, then the pullbacks are isomorphic. Okay, so that's a theorem from homotopy theory that I prove in the book. And what this, now let me see, this should go down, right? Yeah. Okay. Okay, now what this theorem says is that if you look at homotopy classes of maps, then there's a well-defined map into isomorphism classes of vector bundles, isomorphism classes of principal bundles, okay? So, you see, now that we have defined principal bundles over a space, you know, a very good question is, what are all the principal bundles over a particular space, you know? Let's say the space is the sphere, S2, then you can ask what are all the principal G bundles over S2. And that question makes sense only if you look at isomorphism classes. Otherwise, there's just too many of them. Okay? So let's introduce this notation. Okay, so that say okay, PG of X. PG of X, okay, be the isomorphism classes of principal G bundles over X. Okay? And so theorem 6.6 implies that you can define a map from homotopy classes of maps from X to B, right? Okay. So this notation, this means homotopy classes of maps from X to B, H. Okay. Now, whenever you have a map, then you can pull back a bundle. So you can send a map to a bundle. Let me see. What do I want to say? Yeah. So yeah. Let's say you fix a universal bundle. So. So you fix a universal bundle, EG over BG. Okay? Then whenever you have a map, you can pull back this universal bundle. So whenever you have a map, then you can pull back this universal bundle. And you look at its isomorphism class. So you get a map that goes to PGX, right? This is a principal bundle over X, okay? And so you have this map, C. And what theorem 6.6 says is that this is a well-defined map. So if you take two homotopic maps, they go to isomorphic bundles, so it's the same isomorphism class. Okay? Yeah, so I should say, the homotopy class of H will go to the isomorphism class of this bundle, okay? And I get a well-defined map. So theorem 6.6 is you have a well-defined map. Well-defined. Pardon? Oh, you are right. Yeah, it should be X maps to BG, okay? Mapping to the base of the universal bundle. Yeah. Yeah. And, okay, now, the universal bundle has two properties, okay? Now, so tell me what that first property says about this map. What does the first property say? Yeah, the first property says that given any principal bundle over X, there is a map so that the principal bundle is a pullback. Okay? So it says that this map is surjective. Okay? So one, the first property, now this actually goes up. So property one is equivalent to surjectivity. Of phi. And what does property 2 tell you? Yeah, injectivity, okay? So if you have two such maps, then they are homotopic. So that means they belong to the same homotopy class, okay? So it's property 2 is equivalent to the injectivity of phi. And therefore, if you start with the universal bundle, then phi is a bijection. Okay? So phi yeah. So that says that this PG of X as a set is the same as the homotopy classes of maps from X to B. Okay? Now PG of X, that's PG of a space. That's a functor. Okay? To every space, you associate this set. And if you have a map of sets, there's a corresponding map because you can pull back bundles. Okay? So it's a contravariant functor. It's a contravariant functor. Let me see, on CW complexes. Right, and if you have a continuous map of CW complexes, you can pull back bundles. Yeah, so that's your morphism. And this, oops, sorry. Now I should put a BG here, right? Yeah, BG. So this homotopy classes of maps from some CW complex into BG is also a contravariant functor. So if BG is the base of a universal bundle, then these two functors are equal. Okay? And so what that says is that PG is a representable functor. Okay? Because this is much easier to understand, right? Maps into a space than this. Okay? So PG, this functor is equal to this functor. Okay, and so that says i.e. PG. You can represent PG by homotopy classes of maps. PG is representable functor. Okay? Yeah. So this space, BG, is very important, and it's called the classifying space of G, because it classifies principal G bundles. Mm-hmm. Okay. So, mm-hmm. So BG is called a classifying space for G. And now we can prove that BG, the homotopy type of BG is unique. So, because there are many different universal bundles, okay? So there are many different classifying spaces, but for each G, they're all homotopy equivalent. Yeah.
How can we understand BG? For example, G is equal to S1 or S3. How can we understand BG?
That's right. So yeah, so we have to find BG for each group G, okay? And you already know quite a few. So can you tell me an example of BG? Like for G S1, the circle. So you need to find a contractible space on which S1 acts freely, so that the quotient is BG, and you get a principal G bundle. So what is it? Do you have an example of that? Huh? Yeah, because we already showed that S1 acts freely on S infinity, right? And S infinity is contractible. And S infinity is an S1 bundle over CP infinity, okay? So the first example, is that, so S infinity maps to CP infinity, and that's a principal S1 bundle. And S infinity is contractible. So you can take this to be, just a minute. No. There's another thing I have to tell you, and that is that a principal bundle is a universal bundle in the category of CW complexes, if and only if the total space is weakly contractible. So now weakly contractible is weaker than contractible. So when you have a contractible space, all the homotopy groups are zero, right? And that's the definition of weakly contractible, that all the homotopy groups are zero, but it doesn't have to be contractible, okay? So let's make this definition. A topological space X is weakly contractible if pi k of X with any base point equals 0 for all k. For all k. The base point doesn't matter because they're all isomorphic. Let's see, yeah. Now, and so a contractible space is weakly contractible. And then we have this theorem that a principal G bundle from E to B is universal so in the category of CW complexes, okay. So that means we just look at CW complexes if and only if E is weakly contractible. Okay. So that, yeah. So let's just assume these results for now, and then so that says that S infinity over CP infinity is a universal S1 bundle, right? Because S infinity is contractible, therefore weakly contractible.
So does it mean that we can construct the universal bundle as if we are constructing universal coupling in this universal coupling in this category of coupling spaces?
The question is, can you construct universal bundle in the same way that you construct universal covering? No, not the same. Because universal covering, well, a covering space is a very special kind of principal bundle, right? So when you have a covering space, what is the group? The group, I mean, it's always a discrete group, right? Yeah, when you have a covering space, the group is always discrete. It could be Z, it could be Zn, but it won't be S1 or SON, you know, some other Lie groups, yeah. Now, I'm just, right now, can you tell me which blackboard I should go to next? I forgot which blackboard I came from when I was doing this one. I think I was doing this, right? So I think the next one should be this one, right? Yeah.
Is there a general state algorithm to construct a universal
Yeah. Okay, so Milnor constructed a universal bundle for any topological group. And yeah, but you see, actually, for a Lie group, there's a simpler way. Okay? So his construction, it's a little bit complicated, yeah. But for a compact Lie group, you see, we can generalize our construction for S1. Okay? You see, because every compact Lie group embeds into an orthogonal group, right? That's a theorem from Lie groups. Every compact Lie group is a subgroup of an orthogonal group. Okay? If you can construct a universal bundle for a group, you automatically get it for a subgroup. Because if a group acts freely on a contractible space, then any subgroup will also act freely on the contractible space. So that same contractible space can give you a universal bundle for a subgroup. Okay? So for a compact Lie group, you only have to construct a universal bundle for an orthogonal group. And the circle S1 is an orthogonal group. S1 is SO2. So you only have to generalize this construction from 2 to n. Okay? Now for S1, we choose S infinity. So you start with Sn. So you can think of Sn as a linearly independent set of one vector, right? Sn consists of univectors. So each univector is a linearly independent set. Okay? So how do you think we should, what should we replace Sn by if you want to generalize this construction from S1 to SON, SOK. Yeah. For S1, you look at one linearly independent vector in your space, in Rn plus 1. So for SOK, you would look at you would look at k linearly independent vectors. Make them orthogonal too, so orthonormal. Okay, so you look at k linearly independent orthonormal vectors in a Euclidean space Rn. What is the set of all k linearly independent vectors? That's called a frame, a k frame. What is the set of all k frames in a Euclidean space? Well, the Grassmannian is the set of all k planes in a Euclidean space. Yeah, now if you look at all k frames, that's called a Stiefel variety. Yeah. So you can replace S infinity by the infinite Stiefel variety. And that will give you the universal bundle for an orthogonal group. And then any compact Lie group is a subgroup of an orthogonal group. So that will give you the universal bundle for any compact Lie group. Okay? Yeah, so all you need to do is to compute the homotopy groups of the Stiefel variety. And you show that that's always 0. And then you will have a universal bundle for any compact Lie group. Okay? Now, I actually worked all of that out in my book in chapter 1. However, the last time I taught a course like this, I went through all that, and so all that is like very, very interesting homotopy theory, and it makes a very beautiful story, but I didn't get to equivariant cohomology until the semester was half over, And so this time, I think I won't go through all that, okay? So we'll just assume the results about universal bundles. And I want to prove that equivariant cohomology is well defined, and I want to start computing equivariant cohomology, okay? Okay, but yeah, you ask a very good question. Uh-huh. For what? Oh, this theorem. Yeah. Oh, it is in chapter 1. Yes, and I actually proved it using Cartan's mixing diagram. But today I'm going to prove that equivariant cohomology is well defined using Cartan's mixing diagram. So let's see. Okay, yeah, so we have an example, right? We have an example of a universal bundle. Now, can you think of another example, right, for another group? So S infinity to CP infinity is an S1, is a universal S1 bundle. Okay, let's move this up. So we've done another example. Can you think of it? What's another universal bundle? A contractible space on which a group acts freely. We have another example. You don't remember? We haven't done that many examples. How about the group Z, the integers? What space does it act freely on? R, right? The real line. So another example is the real line, which I can draw like this, okay? And it projects down to the circle. And this is R. So, and the group is Z, which acts by translation. So R to R over Z, which is S1. This is a principal Z bundle. Is a universal principal G bundle because R is contractible. All right, and then there are other simple examples. For example, Z2. Because you can replace the complex projective space by the real projective space. And the real projective space you can get by identifying the antipodal points on a sphere. So that's an action of Z2 on the sphere. Okay, but I think I won't talk about that because I want to now show that equivariant cohomology is well defined. Now, let's see, which blackboard? Well, too bad, I've already erased this one. So, yeah. So let's review Cartan's mixing diagram. Okay. So suppose you have a principal bundle, E over B, and then you have a left G space, N. So we have this diagram. Okay. So here, let's see. So we have E over B is a principal G bundle. M is a left G space. Okay? And let's call these three maps alpha, beta, gamma. And these two maps, tau 1, tau 2. They're the natural projections. These two maps, pi 1 and pi 2. Okay? Okay, so what do you remember from last time? If this is a principal G bundle, then what can you say about this? This is it's a fiber bundle. Okay, so it's locally trivial. And what's the fiber of this fiber bundle? It's here, okay, M. Okay. So, yeah, we can conclude that E cross M over G over B is a fiber bundle with fiber M. Okay? Now this also has fiber G. And you can also show that it's locally trivial. Okay? It's very easy to show that this is locally trivial because you know that this is locally trivial. So you can just, and to check local triviality, it's a local question. So you can assume that this is trivial. Say U cross G and over U, okay? And then you just work it out for this case. And then you'll see that this is just a product bundle and this is also a product bundle, okay? So, but, I mean, I can do that, but for lack of time, I'm just not going to do it. I'll just tell you that E cross M over G is a principal G bundle. Okay. Okay, and now using this, we can prove a lemma. Okay. So the lemma is that if is a contractible space on which G acts freely and P over B is a principal G bundle, then you can look at E cross P over G, okay? And it will have the same homotopy type as P over G. Now P over G is going to be B. So that symbol means have the same homotopy type. Okay? So that's the lemma. And I have just a couple minutes, to prove the lemma. Now, so what I'm going to do is I'm going to, replace this M by P. So let's replace the M by P. Okay, and then look at this map. Okay, what can you say about this map? Because now I'm assuming that this is the principal G bundle. So what can you say about this map? It's a fiber bundle. It's a fiber bundle with fiber E. Okay? The fiber is the other corner. This is a fiber bundle with fiber E. And E is contractible. So when you have a fiber bundle, then you have this homotopy exact sequence of the fiber bundle. Okay, so by the homotopy exact sequence of a fiber bundle, you have pi k of the fiber into pi k of E cross P over G into pi k of E of P over G into pi k minus 1 of E. Okay? And because E is contractible, this is 0 and this is 0. And that says that this is an isomorphism for all k. And so therefore these two spaces are weakly contractible. No, sorry, I don't, yeah. Yeah, this is a little bit too strong. I don't want to say that they have the same homotopy type. Okay? That symbol is just that they are weakly homotopy equivalent. That means they have the same homotopy groups. Okay? Yeah, if they have the same homotopy type, then they are homotopy equivalent. But all I'm proving is that they have the same homotopy groups. So they are weakly homotopy equivalent. Okay? And so QED. Okay. Okay, I think I should stop here for 10 minutes, and then we'll finish the proof. Okay. Okay. Yeah. Okay. Yeah. So we'll start again at 120.我这个要不要拿下来？如果要出去的话，要拿下来。